a short introduction. Eric is a PhD student at MIT, advised by Aram Harrow and Mikhail Lukin, and also a former Zapata intern. His research interests include studying how hybrid quantum classical algorithms can be used both in the near term and on early fault-tolerant devices to solve practical problems, particularly how techniques from other fields can be used to study these algorithms. In particular, he's keen on generative models and, as we'll see today, random matrix theory. So today we'll hear about his recent work on critical points in Hamiltonian Agnostic Variational quantum algorithms. Eric?
Thanks for the very nice introduction. Yeah, I'm Eric. I'm a PhD student at MIT. And today I'll talk about this paper I put on the archive last month on critical points in VQE, essentially. And just to make sure we're all on the same page, because I don't know what everyone's background is, let me just explain what VQE is in general and what people have seen in the loss landscapes of these algorithms and why understanding these loss landscapes is important. And then I'll talk about the closest analogous situation in the classical literature where people study complicated loss landscapes, and that's in machine learning. And then I'll say how great machine learning landscapes are and how easy they are to optimize. And then I'll explain how in VQE that's not necessarily the case, to give some contrasting views on these two fields. And then at the very end, I'll corroborate some of this with numerics, all the analytical things I found. Okay. So just to get started, let's give some background on VQE. And you guys have probably seen this slide like 10,000 times in a variety of talks, but here it is again. We're in this NISQ era of quantum computing where we have these noisy intermediate scale quantum computers that are beginning to do things that classical computers can't simulate. So for instance, Google's Sycamore device doing random circuit sampling on 50-something qubits. But really, it's still an open question. Can these devices do anything useful? And really, the most promising class of meta algorithms people have come up with to do this are variational quantum algorithms. So this encompasses a wide class of algorithms that are run on these devices, but the general gist of it is they're motivated by the fact that these devices only have limited coherence times. So you want to spend as little time as possible on your quantum computer because it's really noisy, for instance. So what you do is, depending on the properties of your quantum computer, you prepare some Ansatz state, this ket theta, that depends on your architecture and the problem you're trying to solve, perhaps. And then you phrase the problem you're interested in as a ground state problem. So we want to find the ground state of some problem Hamiltonian H, and then maybe later evaluate some properties of that ground state. And then we optimize this loss function. Okay. And generally, there are two kinds of ansatzes that people use. There are two different approaches to this. They're Hamiltonian agnostic ansatzes. So these are ansatzes that don't depend on your problem, and they're usually motivated by the fact that you want to eke out all the coherence as you possibly can on your quantum computer. So you make your ansatz very structured for your device rather than the problem necessarily. And they're Hamiltonian dependent ansatzes. These are things like QAOA or unitary coupled cluster, where your ansatz directly depends on your Hamiltonian that you're trying to solve. So for instance, in QAOA, you're like rotating under your Hamiltonian every other layer. So generally there are these two approaches, but what unites these approaches is how easy this problem is to solve depends on how easy this loss function is to optimize. So, we've pushed all questions of complexity of whatever problem you're trying to solve to this optimization problem. So understanding how easy this optimization is to optimize is really key to understanding how all this works. So what have people found previously? Probably the most famous kind of result are Barren Plateau results. And there's a gazillion of them at this point that apply to different scenarios. But generally, the way they're stated is if you have a deep Hamiltonian agnostic ansatz, and you start at a random point in your initialization, then effectively your landscape is going to look very flat. So if you're optimizing using something like gradient descent, or really anything that relies on the local properties of your landscape, the landscape looks the same in every direction, so you don't know where to go, and it takes forever to optimize, is the gist of it. So the way I like to think of it is your loss landscape looks like the surface of Tatooine. So that's this picture here. And say you're trying to maximize this loss function. So I guess it's not a loss, it's a cost function, well, minus a loss function. And if you start in the neighborhood of a maximum, then it's really easy to optimize because it's sharply peaked. So you can optimize very easily. But if you start in a random point, the landscape is flat and you don't know where to go. So essentially you just random walk until you hit a peak. So what all these Barren Plateau results really tell us is that you either need a physically motivated ansatz, or at the very least a physically motivated initial guess to get close to the maximum. Otherwise, training these deep Hamiltonian agnostic ansatzes is like essentially impossible in a reasonable amount of time. Okay. So what about the trainability of shallow circuits? Less is known on the analytical side, at least prior to this work, about the trainability of shallow circuits. But numerically, people saw an interesting computational phase transition where shallow circuits tended to be very difficult to train. But then after some critical ansatz depth, so a critical number of parameters in your ansatz, it was very easy to train. So people observed this in two different situations. For Hamiltonian agnostic ansatzes, numerically, it seemed that this critical depth was exponential in n. So for an n qubit problem you're trying to solve, you would need exponential depth to get good local minima. So yeah, what I mean by bad trainability, I mean all the local minima are far from the global minimum. So you get stuck in these spurious local minima, and it's essentially impossible to optimize. So this transition for Hamiltonian agnostic ansatzes seemed to happen at exponential depth. And for Hamiltonian-based ansatzes, it seemed to happen at a much more reasonable depth. So if this holds more generally, this says that not only are deep Hamiltonian agnostic circuits difficult to train, but shallow ones as well. Because not necessarily you'll have a Barren Plateau, but you'll get stuck in a local minimum very far away from where you want to be. So just to illustrate this, because it's important, here is a plot from this Chiani, Lloyd, and Matey paper, which I referenced on the previous slide. So here they're trying to learn unitaries, not necessarily ground states of a Hamiltonian. They're trying to learn a whole unitary. So it's 2 to the n by 2 to the n. So d is 2 to the n. And they find that when you have a number of parameters fewer than d squared, you're in this underparameterized regime. So this is the training as a function of time, and this is the loss, and you get stuck at a very high energy. But then in the overparameterized regime, you essentially always find the ground state, or you find the unitary you're trying to solve for. So there are these two regimes, and what motivated this work was trying to understand these phase transitions analytically. Because if we understood these analytically, then we could design ansatzes such that we're on the good side of this transition, where we can have good local minima and actually have trainable ansatzes. Okay, are there any questions about the setup? I don't know how I can see if people have chatted questions, so I have to rely on people to. Okay, we're good.
No questions on chat. We're good.
Okay, cool. So having given some background on VQE and what motivated this work, let me talk about classical machine learning landscapes. And it's really a miracle of classical machine learning that you can essentially always find the global minimum, even if you're trying to optimize some complicated loss function. So just to illustrate this, so in this Choromanska paper from a few years ago, it was found both analytically and numerically. I mean, it's observed numerically in machine learning all the time that you can optimize easily. But analytically, people found that essentially monotonically with the number of parameters, neural networks are easier and easier to train. So these are some numerics from their paper where they look at classifying MNIST, I think, using models of a variety of sizes. So this is a histogram of local minima for their loss function at these various model sizes. And essentially, as you add more and more parameters, your local minima become better approximators of your global minimum. And you can actually analytically see that this convergence happens at a rate root p. So if you have p parameters, you'll improve at a rate root p in your distribution of local minima. Okay. So this says that classical machine learning, it's really easy to optimize these loss functions. And the way you prove this is really in two steps. So first, there's a variety of these results, but what they all tend to do is show that whatever loss function you're interested in looks like a random field. So what do I mean by that? Essentially, your loss function is a function of your model parameters W, and we're just going to assume they're normalized. So assume they live on a sphere. And these results show that your loss function looks like this random function on the sphere, where the nonlinearities in your model give you an effective Gaussian interaction in your loss function. So effectively, you're optimizing this random Gaussian function. Hopefully that makes sense. But yeah, so this J you can think of as a random Gaussian Hermitian matrix. It comes from this Gaussian orthogonal ensemble, if you know what that is. And once you show that your loss function looks like this random field, it's in this very nice standard mathematical form. And then you can turn the crank using random matrix theory and Morse theory results and actually evaluate what local minima of this kind of function looks like. Okay. So that's the general high level strategy for all of these proofs. And you can say, well, okay, variational algorithms, we're also trying to optimize a very complicated loss function. So do similar results hold? Can we just apply these proofs to VQAs? And the answer is yes at a high level, but actually no, it's very different in the details. And there's really two major differences between VQAs and neural networks that leads to these differences. So as I also, the garbage is being picked up, I guess. So hopefully you don't hear a garbage truck in the background. But so, okay, good. In this neural network construction, I mentioned before that nonlinearities in your model give this effective Gaussian interaction in the random field. You can consider your loss function. Excuse me. But in variational algorithms, we don't have that because our Ansatz is linear, because everything is quantum mechanical. So we don't have this effective Gaussian interaction. It turns out, I'll show later, we have something else. But perhaps the most glaring difference is really that layers of VQA ansatzes aren't fully parameterized. So what do I mean by that? So typically in a variational ansatz, each layer we're applying parameterized time evolution under some fixed Hermitian operator. So we're doing something like e to the I theta poly x, you know, and it's a 2 to the n by 2 to the n size matrix, and we use one parameter to parameterize this whole matrix. In something like machine learning with a linear model, so here's just a diagram of some arbitrary linear model, where each layer we apply a weight matrix, and each line here is an entry of that matrix. We directly tune each neuron. So we directly tune each entry of this weight matrix at each layer. So if we have like a D by D weight matrix that's being applied, we have D squared parameters, as opposed to one parameter for like a 2 to the n by 2 to the n size matrix. So really this key difference, this under parameterization, is what's going to lead to completely different behavior in the local minima landscape for these two kinds of problems. Okay, so hopefully that's a nice high level overview of the general strategy. So just to repeat it, we're first going to show that these loss functions look like random fields, and it'll be a different kind of random field than what we typically see in classical machine learning. And then I'm going to show that the local minima of this random field, due to this underparameterization issue, tends to be really bad and experiences phase transition, at least in the Hamiltonian agnostic case. Okay, so if you have fewer parameters than exponential and n, you tend to have bad local minima, and then you cross a phase transition. Okay. Any questions before I get into the actual overview of the proof? Okay, I'll take silence as a no. Okay, so we're going to consider this class of ansatzes that's slightly arbitrary, but is inspired by actual kinds of ansatzes. So essentially, we're just going to start in an arbitrary stabilizer state, and then have an ansatz composed of random polyrotations. So we randomize everything here just to ensure that our ansatz is independent of the problem we're trying to solve. So the given Hamiltonian that we're trying to find the ground state of. And we'll call Q the number of polyrotations we're performing. But often in VQE, you have parameters that are used multiple times throughout your ansatz. So P will be the number of independent parameters. Okay. And so we have this ansatz that's randomly chosen independent from your problem. And we're just going to assume that your problem is finding the ground state of some physical Hamiltonian. And when I say physical, what I mean is that it's poly decomposition. So this decomposition in terms of poly matrices isn't too inefficient. So it has a reasonable poly decomposition. So I won't get into the details, but effectively that's what we need. And just to make the discussion smoother, we're going to assume it's traceless, but you don't actually need to assume this. It's just to make it nicer. Okay. Does the setup make sense? Because I know it's a lot. Okay.
Wait,
so
Eric,
the first,
could I ask a quick question?
Yeah.
So is this type of analysis easy to do when Q is a little less random? That is like you kind of like repeat rotations in a layer, or like a type of gate in a layer.
So yeah, it's technically not provable in that situation, but I think a lot of the high level things going on in the proof carry over into that situation. Like,
okay,
I think, yeah, it's not necessary that these Q are randomly chosen completely, and numerically, it doesn't seem to be necessary. But yeah, just to make proof more reasonable, we assume that.
Okay, cool, thanks.
No problem. Any other questions?
Yeah, I'm just this may be a very naive one.
Yeah.
The Q, uniform random poly, is that like you have a character I, X, Y, Z in every qubit entry, and then
yeah, so they can be
okay.
very non-local.
Okay.
So again, it's not a very realistic ansatz necessarily, but this is just to help with the proof. But really, so I don't think I have a slide on here going over the proof just in the interests of time. But the idea is your VQA loss function, when we show it looks like a random field. So actually, I'll just go to that slide. This VQA loss function, when you look at the Feynman path integral of this, essentially all you need is that different paths in your path integral look more or less independent from each other. And you can show this when they're actually independent, these rotations. But you know, if you have a deep enough circuit or whatever, it's going to look like this anyway. I mean, not even a deep enough circuit. If you have enough rotations, even if they're being applied in parallel, it'll look somewhat like this. But in that situation, nothing is technically provable because there are a lot of freedom in how you actually design your ansatz. But at least in this, for this randomized ansatz, we have this fully rigorous proof where we show that this VQA loss function can be written as this random field on a torus. So this random field's on a torus because the model parameters, so the parameters for a VQA loss function, they parameterize polyrotation, so they're all periodic. So each parameter is periodic, so we're on the torus. And it turns out, again, going through this procedure where you look at the Feynman path integral and look at moments and stuff, it looks similar to this Wishart random field. And just to make clear what I'm doing here with the VQA loss function, I'm just normalizing the energy to make it unitless and then shifting the landscape to be greater than 0. So the minimum's at 0. But the landscape is going to look the same no matter how it's shifted. So you might notice that I call this J a Wishart random matrix, which I'll explain in a second. But is there any questions, at least at a high level, what we're trying to do here? So we're trying to show that this loss function looks like a random field. Okay, I'm low on time, so I'm going to go more quickly. And this Wishart random field is essentially a multidimensional generalization of a Gaussian matrix. So, or sorry, of a gamma distribution. So if you have a Gaussian matrix, essentially the square of that matrix is a Wishart random field. And the number of squared Gaussians that are being summed in this matrix multiplication is m, the degrees of freedom of this Wishart distribution, or equivalently of this gamma distribution, if you look at it as like a scalar. So if you don't know what a gamma distribution is, it looks like this, and its mean is at m, and then its width is root m. So when you normalize by m, essentially the width of it decreases as 1 over root m. So, okay, why are Wishart matrices important compared to Gaussian matrices in this context? Well, Gaussian matrices, their eigenvalues spread a very wide range. They have eigenvalues that spread like plus or minus some constant. Wishart matrices have a phase transition in their spectrum, essentially, where when m is larger than the size of the matrix, their eigenvalues are concentrated at 1. And otherwise, you get these 0 eigenvalues because it's no longer full rank, and it spreads a wide range. So we have this phase transition already, so you might get an inkling of an idea where the phase transition will come from. And if you go through this whole procedure, it turns out this VQA mapping has m exponentially large than n, assuming your Hamiltonian is reasonable. So this says that if you use this kind of arbitrary ansatz, but probably it also holds for Hamiltonian agnostic ansatzes in general, you'll get this exponentially large degrees of freedom parameter. And there are reasons to believe in the proof that I don't have time to go into, that if your ansatz depends on your problem Hamiltonian, this can be much smaller. And we'll see that numerically. Okay, so just to move more quickly, now we've seen that this this loss function looks like a random field. So let's look at the local minima of this random field. And the way we do that is using this Kac-Rice formula, which I really don't have time to get into, but effectively the TLDR of it is if you know your function value and its derivatives and what they're jointly distributed as, you can find what your local minima look like. So in the Gaussian case, this is actually very simple because your Hessian is a Gaussian matrix and you know what the eigenvalues of Gaussian matrices look like. And so you can show that they have a banded behavior in the local minima because this Hessian stops being positive definite at some point. And when it stops being positive definite at some energy, then you don't have any local minima anymore. And so you put everything together and then you find that your local minima have this like exponential decay law essentially with 1 over root p. So essentially all of your local minima are concentrated at your global minimum. And that's for neural networks, and that's why they're really easy to train. But if you do all this for the Wishart case, effectively you have a much narrower Hessian eigenvalue distribution. And because it's so narrow, this band where this stops being positive definite occurs at a very high energy. And once again, you can put everything together using a lot of math. And you find that effectively your local minima distribution looks like this beta distribution. So that's heavily skewed. So this is peaked at half the mean eigenvalue and is generally proportional to 1 minus p over 2m, where p is the number of parameters you have and m is this exponentially large number. And this width of local minima is very narrow. It's 1 over m. So effectively, we have a phase transition with this order parameter given by P over 2M. So when this gamma, this parameterization ratio, is much smaller than M, it's much smaller than 1, then essentially all of our local minima are half the mean eigenvalue. But when it's greater than 1, then essentially all of the local minima are at the global minimum. So this reproduces this phase transition behavior people had seen numerically beforehand. Okay. So those are the analytic results. Sorry, I rushed a little at the end in the interest of time. But just very quickly, let me show some numerics corroborating this concentration at half the mean eigenvalue. So this is histograms of local minima for this random Ansatz model. These plus or minus root gamma error bars are because we're at finite n, but effectively at half the mean eigenvalue, that's the units of this, all of our local minima are concentrated. And in the Hamiltonian dependent Ansatz case, this seems like very pessimistic, and numerically we see that as well. So this really says that this heuristic understanding of this degrees of freedom parameter being much smaller than we expect in this Hamiltonian dependent case seems to hold. Okay. So with all that said, essentially the whole summary of this, if you got nothing else out of it, is these Hamiltonian agnostic ansatzes seem very difficult to train. So move to Hamiltonian-based ansatzes if you can. And it'd be nice to prove something concrete about these Hamiltonian-based ansatzes, but it's hard to prove things in full rigor when you have an ansatz that depends on your problem. So that's still really an open question. So something I'm really interested in now is applying these techniques to quantum generative models, which at least numerically seem to have very nice optimization landscapes in certain instances. And I'm beginning to see analytically that this also seems to be true, but that's for future work. Okay, great. Thanks for your time. Thanks for having me. Are there any questions?
Thanks for the talk. You can either just ask the question or type it in the chat, and I will read that. Okay, Rob.
Really, really great stuff. I really appreciate the rigor that goes into these kinds of things. What can you say about, and you also please give us your gut feeling even for stuff that's not, provable or anything like that.
Yeah, sure.
About things that are not quite Hamiltonian based, but not completely random either. Like how quickly do you rotate off of the good plane?
Right.
Sort of with that.
So
right?
The heuristic way I think of this proof, and again, because of time constraints, I couldn't really go into the details of this, but essentially where this m comes from, that's exponentially bad. Like I think this model for variational algorithms is a good model, even for Hamiltonian-based ansatzes. What really depends on the details of this proof is this m, which ends up marking this transition point. And essentially this m comes from the fact that generally, if you have a Hamiltonian independent ansatz, you're exploring like the whole Hilbert space equally much. What's a good way to say it? Like you're not really zeroing in on a subspace that is of actual importance to the problem you're trying to solve. You're exploring everything essentially equally much over all of your parameters. So you tend to get stuck in areas that don't actually matter, and gives this really exponentially large m. But if your ansatz depends on your problem, then you can construct your ansatz in a way that explores the important regions of Hilbert space more often, I guess is the easiest way to say it. So depending on what kind of ansatz you're constructing, yeah, I think really generally what you want to try and do is have an ansatz that explores the, some subspace that is interesting and contains what you're trying to find, but is constrained in some way compared to the entire space. I guess is how I would say it.
Okay, that's really cool because there's something, I mean, this stuff is already extremely advanced and really, really neat here, but there's something even further maybe we could start thinking about, which is that there are, at least in chemistry and in other physics areas, there are a lot of structured approximate tensor decompositions of the Hamiltonians. Is like double factorization and cluster model, kind of decompositions of these things, where now your Hamiltonian has much structure that actually looks like the gate circuits that we build, in the gate fabrics and things like that. But it's not exactly the Hamiltonian, it's something close to it and that kind of thing. Right. And so for that, you're coming on something which it looks like it's one of these random, T-design like circuits, but actually you think that it has something to do with a decomposed approximate form of your Hamiltonian. And it just somewhere in there may be some connection. I'm sure it's going to be way harder to work in this environment than in polys and stuff, right? But yeah,
it's definitely something interesting. And yeah, I think there is some weird transition where as your ansatz depends more and more on your problem, this can get better and better. But yeah, it's hard to prove this stuff in full rigor when you're doing that. So I think, at least the way I see it, a good intermediate step are these quantum generative models, which I won't get into, but it's a completely different framework. And depending on your model, it seems like they're much more easy to train compared to these general variational ansatzes. And really understanding why that is might help in showing that, Hamiltonian dependent ansatzes are also pretty easy to train. But that's for future work.
Okay, great. Thank you very much. And with that, we'll end the official part of this QRST. So thank both Rob and Eric for the talk. And I hope to see you all again on the next QRST next month.